Good evening. Okay.
Good
Good
evening,
evening,
sir.
sir.
Good evening. So you have the quiz on coming Monday. Okay. As I announced earlier, so the syllabus will be chapter 2 and 3. So do you have any questions from chapter 2, chapter 3? Any?
Uh, Sir, I was
Yeah.
going through the derivation in the book from back from weak form to strong form, and there they have proved the natural boundary condition also. So, in that, I was having an issue that since we have taken first they have taken a different W, and then they have put the value 0 there, and again proved with a different W for the value of natural boundary condition. I was not able to understand the proof of that.
Will have to see what it has been done in the book. Okay. So I will get back to you by email. Okay. So I have,
Okay, sir.
but maybe in the next class I will have that. Okay. In the beginning of the class I will talk about it. Okay.
Okay, sir.
Yeah. So, but typically, what happens is the natural boundary condition you have already applied, you have in the equation. Yeah. So if you are automatically cancels out.
So your voice is breaking.
Just a minute, guys. Is it okay now?
No, sir.
Just is it okay now, guys?
Yes, sir.
Okay. So I was saying that uh, regarding this, from weak formulation to strong formulation for the boundary condition, I will see how it is in the book. Okay, so accordingly I will uh, uh, discuss during the next class. Okay, in the meantime, as I said earlier, that natural boundary condition is already included in the weak formulation, so it is there. So if you do the reverse, then what happens is the natural boundary condition is already taken care of. Yeah. So only thing is what is not there is the essential boundary condition, and in this essential boundary condition is anyway you have to know that. Yeah. So uh, in weak formulation, uh, uh, we start with a solution which has to satisfy the essential boundary condition. Yeah. Okay, so anyway, I will look at that. I will discuss during the next class. Any other issue? Okay. Okay, if there is no other doubt, then we will solve some problem from chapter 3. Okay. Okay. So here there are some problems that you can look at. All are basically the we have looked at other problems, but let's say problem 3.5. Yeah, so there it says that for the equation of heat conduction, so d over dx Ka dt over dx, right? You have the source x equal to 0. And what it says that it has the boundary condition that's given as T0 equal to 100 and Q bar 10 equal to HT. Yeah. Okay. Now, what is the difference? Here it is Q bar is given. So, of course, this is that really means that X varies from 0 to 10. So you have X equal to 10, you have one boundary, X equal to 0, you have another boundary. So X has varying from 0 to 10. Then you have Q bar. So typically when you say Q bar, this will be basically Q dot N. Yeah. So that means, so if you have a bar like this, yeah, so N here is like this and N here is that way. Yeah. So Q bar here is given by whatever the value. So Q bar at 1 means node 1 is given by N1. So this is N1, this is N2. N1 and N2 are the unit vectors which are perpendicular to the boundary but projecting outside. So it's not projecting inward but outward. So here N2 you have, so accordingly this is given. So basically what happens, as we know that Q is defined as minus K dt over dx, and that really means this is this way, right? If the temperature gradient is more here and temperature is more here, temperature is less there, because of, if that is that dt over dx will be negative, and minus negative multiplied by negative number, that makes it positive. Yeah. So this is how it is defined. And so Q, this really means Q is, you write as I, meaning that x direction, right? Q will be defined, if you want to represent this as a vector, this is how you have to define this. This will be I, right here, like ij and all. So this will be how Q will be. So that means Q bar is given by, Q bar will be Q dot N. So that means Q bar at 1 will be equal to minus K dt over dx, right? And this N is minus I, right? So dot minus I. So this is I dot minus I. So that makes it what? That makes it K dt over dx at x equal to 0, right? So K dt over dx at x equal to 0 is the Q bar 1. Yeah. So if something, instead of writing dt over dx, natural boundary condition, you can write Q bar, where Q bar is has this meaning. So you can also write the natural boundary condition as this, or Q bar. So that's how it is written. So the Q bar 2 is actually Q bar at 10 will be equal to Q dot n at x equal to 10 is equal to minus k dt over dx, right? I dot, and then you have dot, n is I here, so equal to minus k dt over dx at x equal to 10 is given to be whatever the value is given here. So that is ht. Yeah, is equal to ht. So this is what the boundary condition is. Okay. So this is what you have the convective heat transfer. So this is so basically this is H at T equal to HT at T at x equal to 10. So this is what is given. So basically the whatever equation we have, our equation is d over dx k a dt over dx plus sx, okay, is equal to 0, subject to it's given t0 is equal to 100 and minus k dt over dx, yeah, at x equal to 10 is equal to h t at 10. Yeah, so this is what the boundary condition is, and this is called convective heat transfer boundary condition. Rest is fine. Rest, the way you do, you multiply it by W and you do all the operations. You apply this boundary condition and that's done. Yes, the main thing is understanding meaning of Q bar here. Yeah. Any question, guys? Okay, so now 3.6. Okay, so here this problem, heat conduction problem in the circular system, the radial system. So you have this R and equation, heat conduction problem equation in as a function of plus Rs is equal to 0. Yeah? So this equation is given for R. This is R. From here to here, this is R. So this R is variable. This is the outer radius, and this equation tells how the temperature varies as a function of R. So it will have the same function, it will have the same temperature at a particular radius, you know. So 1D problem, but this is in a circular system. Then natural boundary condition is given, and what is given? dt over dr, r equal to 0 equal to 0. So this is the natural boundary condition, and essential boundary condition is given, t r equal to r is equal to 0. Okay. So all the things you know, things which k will be given and s will be given, yeah, r is given, so those things are given. To construct the weak formulation, first of all, so you will follow the same thing basically. So you are going to have like you will have W, which is a function of R, we'll have K, dr, R, dt, dt over dr, sorry, right? Dr, so 0, you will have 0 to R, yes, and then plus 0 to R, and then you have already you have Rs, so you will have Rs dr is equal to 0, and
W.
rest you are going, oh, yeah, W is also there, correct. So W function of R dr is equal to 0. Rest you will do the way you do. Yeah, so uh, these things uh, here, and you have here these things here, uh, the whole thing divided, like you are differentiating, and then so this multiplied by this, so what you will get, you will get WR K multiplied by R dt over dr, and you will have R to 0 minus, yeah, minus, you will have 0 to R, you will have R dt over dr, right? And then you will have this guy, right? So you will have, sorry, so yeah, so yeah, that's correct. And then you have this, so you will have d over dr, and you will have wr times k, yeah, and then you will have dr. So if k is constant, then it can come out. If k is a function of r, then it will be here. Yeah. Okay, so how it is as far as this is concerned, and then this one remains the way it is. Yeah, so I will write that side plus wr, yeah, and then r s dr 0 to l, 0 to r, big R is equal to 0. Yeah, that's it. Or from backside, if you look at it, so what it says, it says dt over dr at, so dt over dr at r equal to 0 is 0. So the second term will be 0, because it says dt over dr at r equal to 0 is equal to 0. So second term will be 0. First term, t at r equal to 0. So since at r equal to r, big R, t is given, so wr will be 0. So we will see that in both the cases it will be 0, right? So in one case this will hold, and because of that we can write here that this tells you that wr is equal to 0. So because of that, when you put big R here, this will be 0. When you put here this value here, dt over dr, then this becomes 0. So both of them will be 0. So this whole thing becomes 0. And then you have this guy. Okay, so in this problem, k is constant, so you can take this outside, so your problem becomes, or 0 to r, k comes outside, and then you have r dt over dr, dw dr, so r dw over dr, dt over dr is equal to w function of r, then rs dr, 0 to r. So this is the your weak formulation. Yeah. Now it says use quadratic trial solution. T is equal to alpha naught plus alpha 1r plus alpha 2r square and weight function of the same form to obtain the solution of the weak form. Yeah. So of course at t0 is 0, since t is 0 equal to 0, that means alpha not equal to 0, so you have to put that. So that tells us that t equal to alpha 1r plus alpha 2r square. Similarly, wr, let's say beta naught plus beta 1r plus beta 2r square. Yeah, and since w at 0 has to be 0 because t is given there, so we have w 0 equal to 0, and that makes it beta not equal to 0. So you have the same formulation. Yeah, and then you will do the analysis. Now the solve differential equation with the boundary condition and show that temperature distribution along the
Sir,
radius
sir,
is given.
sir,
Yeah, yeah.
T at 0 is not 0. T at R is 0. Alpha 1 will become 0.
Oh, yeah, yeah. Okay, okay. Yes, yes, yes. Thanks for that. So, yeah, yeah. So this, okay, our boundary condition is WL equal to 0.
And sir, one more thing.
Yeah, yeah.
So when like if you or T is both the sides we are given like u, then we'll take weight function 0 on both sides. Like if suppose we are given T on 0 also and R also, then we'll take W both places 0.
Sure, sure.
Okay.
Correct, correct. Okay, so you put W L equal to 0. Uh, yeah, accordingly you have to find out what the beta will be, so in that case you can put the beta in that case. Yeah, so if that is the case, then what happens, we put L here, sorry, not L but R. So here R is 0, say beta naught plus beta 1L plus beta 2L square is equal to, I always write a L. So here it is. Okay. So beta naught is becomes minus beta naught R minus beta 2 R squared. So you put that value. So WR is equal to minus beta naught R minus beta 2 R squared plus, I think this should be beta 1, beta 2. Beta 1 R plus beta 1, beta 2 R squared. So it will be simply beta 1 R minus big R plus beta 2 a small r square minus big R square. So this is how WR will be. Yeah. So you have this. And accordingly, you will put those values and you can find out and then you solve the differential equation. And you have to prove that t as a function of r is equal to s over 4k r square minus r square. So to prove, so you can do it, and rest is solving the problem, putting the w and t. Yeah. So all those things you have to do, please do yourself. Here just method we will discuss so that we can maximize number of problems. Okay, so but any question, guys?
Yes, sir. Sir, in the same question, when I tried doing it, it's giving like at the end when we make it 0, then like I'm not able to understand that how is it done. Like I have obtained equation
Hmm.
and I'm not able to make it 0. Like it can be seen that alpha naught is coming SR square by 4k, but something is going wrong, which I'm not able to understand.
You are saying this, you are not getting the value of alpha 1 and 2?
Sir, actually, what happens is when at the end, when we were proving from weak form to strong form, then we had done this. We had taken Wx to be of the form Ea dt by du by dx plus b something. So then we had said that this becomes zero because it's a square and psi is greater than zero. So, sir, here I'm getting different things. I mean, within the integral, I'm getting two different things, and it is becoming equal to zero. But how can I say that I can make it zero, like inside, that others are not like negative?
Actually, I'm not getting you. So tell me one thing. So here, when you have t is a function of two things. Sorry. So go back.
No, sir. I
We
think
have,
now it's fine. Actually, I had confused. Other things were positive, so only one thing can be made zero. No, sir. It's fine
fine,
now.
fine.
Yes,
Okay.
yes.
Okay. Yeah. Okay. So just do it again. Okay. So if you face any problem, just let me know. Okay. Tomorrow or day after. Okay. Okay. So, okay. Next is problem 3.7. And given the strong form for the circular bar in torsion. Okay. So the strong form for torsion is given. This is same as the 2D the 1D elasticity that the inaxial tension problem. It is exactly the same one. Yeah. So only thing is, instead of J, yeah, you have area. So remember, it has the same type of form, d over dx, a, e, and du over dx, and you have b, x equal to 0. So same form. So j becomes a, g here. Instead of angle of twist, you have the displacement, and then again this kind. So you can also derive the same thing actually. Yeah. And natural boundary condition is given, which is m. It says m at x equal to L is equal to jg d phi over dx at x equal to L is given to be m bar. So which is a constant. A constant is given. This you have to apply, and then essential boundary condition, it says phi at x equal to 0 is equal to phi bar. So this is also a constant. So these two values are given. You have to currently put, and you have to do it. Okay, where mx distributed moments per unit length. This is some distributed moment per unit length. M is a torsion moment, phi is angle of rotation, g is the shear modulus, j is the polar moment of inertia. Okay, so all those things you know. Construct the weak form of the circular bar in torsion. Assume that mx equal to 0 and integrate the differential equation given above. Find the integration constant Ug boundary using the boundary condition. Now it is also telling you to solve it. It's very easy actually. Yeah. So also you're telling first you have to do the weak form. Okay. First part is a weak form is what. So it is very easy. Multiply by W and do the things you do. Apply this boundary condition. That's it. So it is easy. So you do yourself. Now part B saying that if mx equal to 0, okay, and then it says integrate and find out how the phi is. So it's very easy, right? So then you have what? You have d over dx, and you have jg d phi over dx is equal to 0, and then you have jg d phi over dx equal to some constant you get. right, is equal to some constant, let's say called C1, and then you have d phi over dx equal to C1 over Jg, and that means phi is equal to C1 over Jg and x plus C naught, assuming that J and G both are constant. This is how it will look like. Yeah? So direct integration, you get this. If J, G are not constant, then you get complicated solution in terms of log and something can get. Yeah. Any question, guys? So far, so good. Okay. Now, problem 3.8. It says consider a problem on, so 0 to x L, which has the solution of the form. So ux equal to minus half lambda x over L this
So
is
your voice is breaking.
You are not audible to us, sir.
if x is less than L over 2, and then uh, x
So your voice is completely breaking.
minus you guys are with me?
Yes, sir.
Yes, sir.
Yes, sir.
Sorry guys, there's some problem. Sorry guys, are you with me?
Yes, sir.
Yeah, sorry about that, man. Sorry guys, this network problem, this is since this is at night, and I drive, so I thought that I come home and then I mean, do this class, so but earlier the internet connection was good, but today somehow it is getting problem. Although I'm using tried two different things, the 4G and the Wi-Fi I have, but still I have problem. Please bear with me. Now, so the problem number 3.8 that we are looking at, and this is what it is given. We have U defined for different range. So x for x greater than L over 2, this is given. Okay. So this is you have to prove. First is so that lambda greater than 0. For lambda greater than 0, the solution U is U.
Sir, isn't there one more term? Like in the second UX?
Oh, right, correct. Oh, yeah. So here you have minus 1 over 2 to the power lambda x over L. So this is the whole thing. From here, this is the whole thing. Okay. So first you have to prove that for lambda greater than 0, U belongs to C naught. So, and we will discuss the meaning, and B for 0 greater less than lambda less than 1/2, you have to prove that solution Ux is not in H1. So what is the meaning? Basically, the best thing is to you can plot, for example. Yeah. So if you plot, you will know automatically. You know that this is a linear given the value of lambda. So look at Ux being half lambda x over L. So if you plot, what happens? This one is for x less than equal to half. So if you plot, yeah, so this is x and this is ux. So depending on lambda, yeah, either if lambda is more than 0, then what happens? You have this at x equal to 0, this value will be 0, and then at x equal to L over 2, you will have some value, negative value. So this is going, if you try to plot, this will be how it will be going like this, right? So till what? Till this value will be x L over 2. So it will go from here to here, yeah, and linear, it will linear. Second part, if you look, it says ux is equal to x over L minus half lambda minus half lambda x over L. So if you here, what do you see here? Here, this one is linear for sure. Here, this becomes non-linear, but still you have this part here. Yeah? So this part is being added here. This part is linear, this is non-linear. So you will see that what we will see here, that this is a continuous, right? X to power lambda, if lambda is greater than 0, and this guy is the whole thing is greater than 0, right? So this will be continuous. Only thing is it will not be non-linear, it will not align, it will either it will be like this or like that, depending on the values. So we have to see the continuity here, right? That's the main thing we have to see. Rest is it will be continuous, we know that, right? So continuity, how will you find out? So we find out at from the first one, UL over 2 is equal to minus half lambda, and you have half, because if you put L over 2 here, so it becomes half. So it will be minus half and half lambda. So simply it will be minus 1 over 2 lambda plus 1. So this is what the value is. From this value is for x greater than L over 2. Yeah, so if you use this one, UL over 2, we should get the same value. If we get the same value, it will be C naught, otherwise it will not, right? So UL over 2, we get 1 over 2, minus 1 over 2. So this cancels out, so it becomes 0, minus, you have the same thing here. Yeah, so minus half lambda, half, so minus 1 over 2 lambda plus 1. So both are the same value at x equal to L over 2. So that means it will be continuous. If you put x equal to L, then what happens? Here, if you put x equal to L, so this becomes 1 minus half, so half L, yeah, and then just to know what the value will be, right? So from here, if you see the value will be some I think it will go to 0 probably. So we can check how that will be. So just hold on. So U at L will be equal to L over L minus half lambda minus lambda L over L. Excuse me, guys, just a minute. Yeah. So you guys are with me?
Yes, sir.
Yes, sir.
Okay. Okay. So what we get is 1 minus half lambda minus half lambda 1. And you get half lambda minus half lambda is equal to 0. So UL equal to 0. Yeah. And that really means this will go from here to here, and then from here this will either, so let us say this is L, this will either go like this or go like this. Yeah, so we have to see how it is going, but looking at this is continuous, right? Meaning that it has only one kink, otherwise it goes like this. So that really means we can this X is C not continuous, right? That we know, right, from the definition. Second part, when it says to check, to show that, we have to show that for 0 lambda half U belongs to, does not belong to H1. If you want to do that, then we have to check accordingly. So what is the meaning of H1? H1 has certain property we should have. And what is the property? We call H1 because this is kinematically admissible. Kinematically admissible. So first, we want it to be, has to belong to C naught, or basically what we want is du over dx. Especially like if we integrate it, right? If we integrate over the whole domain, and then we want its derivative to be a square integrable, right? So this is the main thing. As you know that in equations, this is what we get, du over dx terms we get. And this is the requirement that it has to be a square integrable. So that means du over dx, it should not happen that du over dx itself approaches infinity. Yeah, so in that case, it will be, u will not be a solution in that. You cannot do the operations basically because of that. U cannot be such a way that its derivative is not a square differentiable. Means our idea is that d over dx square dx has to be less than infinity. So this is the requirement of u. Yeah, and that we call it, what we call it? We call it, this is kinematically admissible. So these things plus u has to satisfy boundary conditions. Yeah. So u has to satisfy boundary condition, and u, the derivative of u should also be a square integrable. Yeah. So now you have to check whether derivative of that is finite or not. That's what you have to do. Yeah. And for that, what you will do, you have to find out du over dx will be equal to, we will have minus half lambda, right, 1 over L, right? So that is for x less than equal to L over 2. So this is straightforward, regardless of what the value of lambda is. For x less than L over 2, this is what the value will be, right? And this is equal to, for greater than x over L, this is complicated. It becomes x lambda here, x over L minus half lambda minus 1 and minus half
Sir, 1 by
lambda.
L also.
Yeah. You are right. Okay. Okay, so then we have 1 over L coming from this guy, so multiplied by 1 over L, and then minus you have half lambda 1 over L, and this is true for x greater than L over 2. Yeah. Okay, now here we have to now look at how the values are, so if you plot it, you will know automatically, right? So let's try to plot it. So we can write du over dx equal to minus half lambda 1 over L. So, and this is still x less than equal to L over 2. So du over dx equal to, so we have okay, so simplification, I think it is what the simplified already, probably. Okay, so just let's not write. We just find out at du over dx at x equal to like x equal to L over 2. Let's check what the value is. Yeah. So from the first one is equal to the same value. It will be the same value if we apply the first one. So let's apply the first one. From this we get is equal to the same value, half lambda 1 over L. However, if we apply this value, yeah, so at the boundary, at the x equal to L over 2, then what happens? So du over dx, yeah, at x equal to L over 2 will equal to, we have lambda, and then we have what? This one is, it becomes half, yeah. So even we don't put that, we just we can put a half also. Let's do it. Yeah. So the value at least we will know. So L over 2 divided by L, so it becomes half. So it becomes a half minus half, and this lambda minus 1, right? Okay, and then we have 1 over L minus half lambda 1 over L. See here, this becomes 0. Yeah, 0, but what is the value here? So if lambda, it now depends on lambda actually, right? So if you have the value lambda, which is, here we get 0, so we get lambda, so du over dx, yeah, and is equal to, we get lambda, and then we have the value, and then we have lambda minus 1. Okay, over L minus half lambda L. Yeah. Now this one, you can see that if lambda greater than 1, if lambda greater than 1, then what happens? Then this will be 0. Otherwise, this will have problem, right? So if you look at, if lambda greater than, less than 1, then du over dx becomes what? Du over dx is not defined. Not defined means it tends to infinity, right? So this will be equal to infinity actually because of this thing. Yeah. Okay, guys, you are with me?
Yes, sir.
Yeah. Okay. So basically, what happens is in this case, like if you try to plot x du over dx, then we have from first one we have one here, and then suddenly it will jump, you know. So suddenly it will be in some value which will be infinity. Yeah. So here we get some infinity value, right? And then maybe at x equal to L, you get the same value. So you can actually find out if you put x equal to L, then you will have some value. Yeah, there will be some value, right? So it will be finite probably when, so this will be something coming like this. So at this, it is sudden jump, and it's not that only sudden jump, but this portion goes to infinity. So it is not a square integrable. Yeah. So not, that means du over dx not square integrable. Integrable for 0 lambda half. In fact, for even lambda equal to 1 also probably this will be the same thing. Yeah. But you also have this, no, still because of we have to see the actual value basically. I think when you have lambda, it may be possible you have to do further analysis. You have to see what happens if lambda you have 0. This is we just did, we just looked at without plotting it. I mean, we just have some idea, but rough idea basically.
So, like,
But
won't there be a lot of graphs for different lambdas?
so that's why I'm saying, so at lambda equal to half you have to see, okay, how maybe at that it becomes 0, you know. So I mean I mean uh, for different lambda you have to assume and see how it goes. Yeah. So right now we have just seen for in general we know that if lambda is less than 1, then there is a problem. Yeah. But actual value what it will be, we have to look at. So exactly if we have because this guy may be as we at this point we have to look at whether it is going to infinity or not. I mean, finally it comes to whether this is integrable or not. Du over dx is a square integrable or not, right? So finally we have to look at that. But I think the problem says that you have to just prove that for this, just for this range, u is not does not belong to H1. So that means you have to just check for this range only. Yeah, it's not that you have to find out the range. If the range is given, I mean not range, but the value actually. So I mean, yeah, range of values for lambda only. This is given, and for that you have to prove that this is not a member of H1. So that is fine. Okay, but even if lambda is less than 1, yeah, so for that also this may be valid, but you have to look at the actual plot basically, that whatever it gives you. Yeah, fine guys. Any question on that? It's all right. Okay. So you don't have to have many plots for different lambda, because main thing is if you check at x equal to L, there itself, if one of these two at x, the value is discontinuous for sure, and when it approaches infinity, automatically at this point you cannot integrate basically. Yeah, and because of that there will be a problem. Yeah, and hence it will not be there. So you have to just check at L equal to x equal to L over 2 only. Is okay? Everybody comfortable with it? Okay, all others are similar, not difficult one, so you can do it. I take up the last 3.9. We have done already. Okay, so I will take up this 3.10, and it says that a body subject to temperature field Tx, the temperature causes expansion of the bar and stays law. So sigma x. So this thermoelasticity problem, Ex and then epsilon x minus alpha x dx. So you have like this, and then for that you have to find out subject to a temperature. So Tx is given. Yeah, and this is the elasticity problem, and this is figure 3.2. Okay, this elastic bar basically. So what you have is d over dx Ea du over dx, right, plus b x equal to 0. So this is what it is, and then you have this sigma x is given by this, right? So what so basically the you have to implement that, so somewhere. Yeah, so this one is sigma x. So this strain law is given like that. So when you derive it, there you have to do the same thing. So here this may not evaluate this. Okay, so you have to first derive this itself. So this is not valid, because why? Because you have a different stress strain relationship. So sigma equal to E times Ex, that we called it the Hooke's law, is not applicable anymore. You have this law that you have to implement, and accordingly when you have to look at like this. Yeah, so you have remember you had d over dx sigma a, right, plus bx equal to 0. That's what the basic that we found out. So this is had sigma a, this was uh, sigma a plus d sigma a over dx. Yeah, you got that. And then you have bx here. Okay, so this we know. Now relationship is sigma x is equal to E x, and then we have strain terms. So then you have epsilon x minus alpha x dx, this term, right? So this whole thing we have to put it here now. So we have d over dx and then ex epsilon x minus alpha x dx, right? So we have this, and this is sigma multiplied by a, right? So we have a here, and then plus bx is equal to 0. Yeah, or d over dx and e, we can have a first, then e as a function of x. A is also can be a function of x, and you have du over dx minus alpha x dx, right? So you go like this and plus dx equal to 0. Yeah, so this is the equation you get. Yeah, so you can see that this will be a little different kind of equation you get. So you will have two terms here, and accordingly you have to proceed. Yeah. So if you know alpha x to begin with, if you know tx to begin with, then if you know it ex as well, a as well, so you multiply by this, and you take derivative of this. So this will be a function of x, and then this will be as like it will just add up to bx. B is also a function of x, and so you can treat that. So basically what happens is you can have d over dx, and you have a ex. So you have a ex du over dx. So du over dx, right? And then we have plus d over dx, plus we have d over dx, and then we have all of this a e alpha t. So I think this has to be minus. Yeah. So a e x alpha x dx. We have this. Yeah, and then you have bx is equal to 0. So here we have derivative, here the derivative of u term here. But here if you say u is not coming, so all these can be a function of x. So basically you can treat these as a body force. That's it. Yeah. So your becomes d over dx a e du over dx. Yeah, plus we can write which is a function body force, a function, to we can write sx, for example, is equal to 0, where sx equal to bx minus d over dx a e alpha t. Yeah. So if you are given a as a function of x, e as a function of f, x alpha as a function of x, t as a function of x, automatically you will get some function, another function which is function of x, that will be here, and then you can easily you can do work on it. You can get the values, right? The rest you can do very easily. You got it? So basically a thermal strain is a kind of a body force which is generated inside the bar, and that creates stresses. Yeah. Any question, guys? Any question now? Okay.
Sir, not in this, but there was one question, I think 2.2, where we had to find the net K. And you had found the global matrix and everything, but how will we find the net from global stiffness matrix? Like directly by series and parallel relation, we can find that, but from the global matrix, how will we find the net K?
Just 2.2 you are saying?
Just a second. Yes, sir, 2.2. I think it was 2. Yes, sir, 2.2 only.
2.2, the equivalent stiffness?
Yes,
of
sir, yes, sir.
Okay. Just a minute. The equivalent stiffness of aligned the is it k equal to 5 E T A B
Yes, sir.
over A
Yes, sir.
plus the same one where E is a Young's modulus and T is the width of the bar. And then
Yes, sir.
so where are
So
you facing problem?
directly I have found, but from using the global stiffness matrix, like you had found by connectivity and all. So from that, how will we get this? Like using like directly, I had got the formula 1 upon k equals to 2 upon k1 plus 1 upon 2 k2, this sort. But this was directly which I got. If we have a difficult system, then probably I'll not be able to do the series and parallel thing easily.
No. So I think in one of the classes, tutorial classes, I did it, right? So I showed the how to proceed this.
So
So,
just a
we
second.
created,
I'll see again.
yeah. So we created the global distribution matrix for that. This is the way to solve it.
Sir,
Yeah.
but then from that, how will we find the equivalent? Like
How
you
to
have
find?
found this global stiffness matrix, that is fine.
Okay. So so it depends on the formulation, how we formulate it. So I guess how we formulated was we fixed like this, right? We fixed this one, yeah, and we gave a unit force here, right? That's what we did.
Yes, sir. Ourselves a unit displacement you had assumed.
Yeah, unit displacement was assumed, right? So if you assume this u, let us say we call it L, L equal to 1. That's what we assume, right? So whatever the force required here, will be the value of K, right?
Oh, okay. That would be the net K. Okay, sir.
Yeah. That will be net K. Yeah. So
Okay,
I
thank you,
remember
sir.
I discussed this. Yeah. I remember I discussed it. I said that whatever the force here you get K. Yeah.
So probably I was not able to understand that that's the net. Okay.
Yeah. Okay. Any other question, guys? Okay, if there is no question, okay, thank you very much. Okay, I will see you tomorrow. Okay.
Thank you, sir.
Okay, thank you very much. Thank you very much.
Thank you, sir.